What's up, guys? Welcome back to another Algebra 2 lesson here as we are extending our knowledge about the content of solving quadratic equations. So up to this point, we've taken a look at 4 methods for solving quadratic equations. We've looked at factoring, using the square root property of equality or following reverse order of operations. We have looked at completing the square and using the quadratic formula. We looked at those individually, and basically what we want is we want to come up with the most efficient and effective way to solve an equation for accuracy, but also for the amount of time that it's going to take us to solve a problem. So I want to give you guys some tips or a guide for choosing a method to solve, because not all problems are going to tell you to solve this way. So there's some steps that if we follow, it's going to make things a little bit easier, a little bit quicker, and more efficient for us. So this is going to be for any quadratic that's in standard form and is equal to 0. If this is the case and b is equal to 0, we want to use square roots or reverse order of operations. So if we had a problem, let's say x squared plus 9 equal to 0. We want to solve this using reverse order of operations, subtract the 9, and then use a square root in order to get x by itself. That's going to be the fastest and most efficient way. There's no b value. If it was written in an expanded form of this and there's still no b value, so let's say we have, 3x minus 4 quantity squared plus 27 equals 0, we would still want to follow this through the reverse order of operations, SADMAP, use square roots, because that's kind of a different form. This is what would be closer to the vertex form of this equation. So both of those cases, we want to follow the reverse order of operations and use the square root property of equality. If c is equal to 0, we want to factor, and we want to factor this specifically using the GCF. So let's say I had x squared, that's not an x squared, let's change that up. Let's make this x squared plus 3x equals 0. Here I would want to go ahead and take out the GCF, which would be x. Then I can set my factors equal to 0 and solve quickly there. So I'm going to factor this specifically using the GCF. My third scenario, and you'll notice there's a lot going on here. This is really the only time that we would want to complete the square. So if a is equal to 1, b is an even number, and c is not equal to 0, the quickest and most efficient way is to complete the square. So you can do it in other scenarios, but this would probably be the only way that we want to get to the complete the square method. So if we have, let's say, x squared plus 4x minus 8 equals 0. This might be one that we would want to complete the square on. Okay, it's tough to factor. We could use the quadratic formula. Completing the square here is going to be pretty quick and efficient. If none of these things are true, we are going to either want to factor or use the quadratic formula, whichever is more efficient in that problem. So if this was, let's say we had x squared minus x plus, this is x squared minus x minus 2 equals 0. This is super easy to factor, or should be for us. X minus 2, x plus 1, we want to factor that. That's quick and that's easy. If it was maybe 3x squared plus 4x minus 9 equal to 0, maybe we can factor this, maybe we can't. But this is probably not very easy for us to factor, so we probably want to use the quadratic formula in that case. It's going to be a little bit quicker. If you get really good at factoring imaginary numbers, factoring is going to be the way to go more often than not. It can definitely save you some time if you factor quickly and efficiently. So these are kind of some guidelines to choosing a quadratic method or a solving method that's going to allow you to complete problems quickly, efficiently, and with accuracy. Now let's move on and let's do a little bit of work with some word problems. So you can go ahead and read the information that they give us here about the equation to represent gravity, the effect of gravity on an object. And so you've probably seen this equation in physics if you've taken physics, maybe in some of your other science classes you've seen this. Depending on what units we're in, we're going to use one of these two problems or equations here to represent the height of an object after a certain amount of seconds since it was either thrown upward or released downward. So the height for in feet would be h of t equal to negative 16t squared plus v sub 0 times t plus h sub 0, where v sub 0 is the initial velocity, so how fast it would be moving at the instant that it was released, whether that's downward or thrown upward. H sub 0 is the initial height, so the location where that object was released. Over here, we have h of t in respect to meters. The only difference is the leading coefficient, because that is the effect of gravity on an object in meters per second as opposed to feet per second. So these two equations we can use to help us identify the height of an object. Now, they're quadratic equations, so we're going to be able to use our quadratic solving methods. So let's take a look at an example here. Problem 7 says, a person standing on a cliff 60 feet high throws a ball upward with an initial velocity of 102 feet per second. Assume the ball is released 5 feet above where the person is standing. Find the height of the object after 3 seconds and how many seconds until the ball hits the ground at the base of the cliff. So what we need to do here is we need to take this information, we need to choose an equation, substitute it into an equation, and solve. So h of t, this is going to be in feet. So we're going to use this equation over here, the negative 16t squared plus v sub 0 times t plus h sub 0. We're going to use this equation to represent the height after t seconds. So I'm going to substitute in what I know. Here's my equation. H sub t, or h of t, is equal to negative 16t squared. We don't know time yet. We'll come back to that. Plus v sub 0 is initial velocity. And they gave us the initial velocity. So this ball was being thrown upward, meaning this is a positive number. It's going to be 102 feet per second. So 102 times t. Plus h sub 0 is the height that it was initially at, which would be 5 feet above where the person is standing, or 5 feet above the ground. So plus 5. So this is our equation that we're going to use to answer the two questions. So question A says, find the height of the object after 3 seconds. This should be an easy solution for us, because what they give us is seconds, which is our t value. So we essentially want to find h of t. So we can substitute 3 in for t, and then we can solve. So if we want to show our work, this would be all the work that we need to show. And then we can go to the calculator. Now we want to type in exactly what we see. So negative 16 times 3 squared plus 102 times 3 plus 5. It's a very basic problem, the substitution that we've been doing in the beginning of the year. And so what we get is 167 feet. We're finding the height, so this is feet above the ground, or wherever the person is standing. So after 3 seconds, the object's going to be 167 feet above the ground. Now in part B is where we have to do a little bit more work. Part B says to find out how many seconds, so now we have to solve for t, until the ball hits the ground. So how many seconds until the ball hits the ground at the base of the cliff? So, sorry, I made a mistake. We're going to have to go back and we're going to have to fix this problem. I apologize. I left out a piece of information here. Our individual is standing on a cliff. So if I drew a rough sketch, here's my cliff, here's my individual, here's the individual throwing the ball. So the ball goes from his hand and goes this way down to the ground. Okay, so what I didn't account for in the first problem is that the cliff is 60 feet high, and then the ball is another 5 feet high. So I made a mistake here. My initial height should not just be 5. It should be the height of the cliff plus the height of the individual. So it should be 65 feet. So sorry about that. We need to make sure we account in all of the pieces of information. So let me go back and let me fix this problem right here. So this should be a plus 65. So my answer should actually have been that the ball after 3 seconds is 227 feet above the ground. So if this was at 3 seconds, we don't know exactly where it's at, but if this was 3 seconds right here, after 3 seconds, then the ball is 227 feet above the ground. That is also going to change what I was going to do for B, but it's something we can still work with. So let's go back to part B, where we want to find how many seconds until the ball hits the ground. So we need to solve for T. Now the ground would be height of 0. The height at the ground is going to be 0. So what we know is h of t is going to equal 0, or essentially negative 16t squared plus 102t plus 65 equals 0. So now we want to solve this equation. So if we look at our clues to choosing a method, B's not 0, C's not 0, it's definitely not number 3. Well, it could be, but we're not going to make it number 3. What we want to do here is we want to factor if this is easy for us to factor, or we want to use the quadratic equation. And we may look at this and think this is not very easy to factor. So let's go ahead and use the quadratic equation. So the quadratic equation would be negative b. Our b value is 102, so negative 102, plus or minus the square root of b squared, so 102 squared, minus 4, times a, which is negative 16, times c, which is 65, all over 2a, which again is 2 times negative 16. So now we want to simplify if we can. So 102 squared minus 4 times negative 16 times 65. I'm simplifying what's in the square root. So what I would come up with here is t equals negative 102 plus or minus the square root of 14,564 over negative 32. This is a big expression here, but we can't evaluate this expression. So I could try to see if 1465 is a perfect square. Sorry, 14,564 is a perfect square. It's not. So we know that our answer is going to be slightly rounded here. We do want to go ahead and round our word problems. A lot of the times when we solve, we give the exact answer. Let's round this problem so we get a better representation of what this number actually means. So one of our answers could be is negative 102 plus the square root of 14,564. Sorry, I typed in negative 120. Let's change this to negative 102 plus 14,564. And then that number divided by a negative 32. So one of our solutions for t, let's go ahead and write this out, and let's round to 2 decimals, would be approximately negative 0.58 seconds. Well, if we think about this, this cannot be true. We can't have negative time here. It's a solution for the equation, but it doesn't make sense with our problem, our scenario. So what we need to do is go back and find the other answer for t. So notice that this is plus or minus. So now I'm going to go ahead and do negative 102 minus the square root of 14,564 and divide that number by negative 32 and round this to 2 decimals. So t is approximately 6.96 seconds. This answer makes more sense. So this is going to be the answer that we choose to represent our problem. So the person throws the ball, it follows this path represented by this equation, and then after just under 7 seconds, it's going to make impact with the ground. So here what we have done is taken the information from the word problem, substituted into an equation that we were given, then used the quadratic formula to find a solution for t. Let's look at problem number 8. Problem number 8 is a little bit different. Problem 8 says from 1995 to 2002, the amount A of annual international telephone calls or traffic in billions of minutes can be modeled by A equals 0.3x squared plus 8.9x plus 61.8, where x sub 0 or x equals 0 represents the year 1995. If this trend continues, in what year will the annual number of minutes reach or surpass 275 billion minutes? So notice a couple of things. That this equation is giving us in billions of minutes. It's already given it to us in billions of minutes. So our answer needs to be in billions of minutes. The equation is in billions of minutes. We don't have to do any conversions there. Also notice that x equals 0 represents 1995. That's going to be important when we come back to it. Okay? We want to figure out when the annual number of minutes will reach or surpass 275 billion. So what they're giving us is A. So 275, this equation again is already in billions, equals 0.3 x squared plus 8.9 x plus 61.8. So this is a quadratic equation that we need to find a solution for. Judging by the looks of this equation, if it's decimals, it's probably not going to be very easy for us to factor. Maybe we can factor, but it might not be the easiest method for us to use. We're probably not going to want to use the completing the square method here. We have a leading coefficient of other than 1. It's got a b value, so we're not going to use square roots to solve. So what we can look at doing is the quadratic formula. So in order to do the quadratic formula, we need to make sure that this equation is equal to 0. So we're going to subtract 275 from both sides. So 61.8 minus 275 is negative 213.2, and this is going to give us a new constant for our equation. So 0.3x squared plus 8.9x minus 213.2 equals 0. Now we can use the quadratic formula. So x is going to equal negative b, my b value is 8.9, plus or minus the square root of b squared, so 8.9 squared, minus 4 times a, which is 0.3, times c, which is negative 213.2. Don't forget that negative that goes with c. All over 2 times 0.3. So if we want to simplify this, let me go ahead and type in what's going to be inside the square root to see if that comes out to a nice perfect square. If it does, we can simplify this by hand. If not, we know our answer is going to be rounded. We're going to use the calculator. So I want to type in just the discriminant here. I'm going to type in just the discriminant, what's inside the square root. It's going to be a positive number, so we know that we're going to get two real answers with this. It's a decimal, so they're going to be irrational numbers here. It's not a perfect square. So we don't know how to square root 335.05, so we're going to let the calculator do that. So we simplified the equation. Now we're going to let the calculator work. So let's do negative 8.9, and let's try plus the square root of 335.05. And then that is going to be divided by 0.6. And so our solution here is going to be a positive answer. So this is going to represent our problem appropriately. Last time we had a negative answer, so I had to find the second option. This is going to be a positive answer, so this is going to represent a positive year. So we can use this answer. So x is approximately 15.675. Now this is not our answer, because remember, x sub 0 is the year 1995. So we want to add this to 1995. If we add this to 1995, we get the year that this will surpass 275 billion minutes. So this is going to be during the year 2010. So in both of these cases, we had an equation that we were given. We substituted in the given information, and then we picked a method. The easiest method in both of these options would be the quadratic formula, and we were able to solve for that quadratic equation. This looks like a good place to stop for part 3 of our notes. As always, thank you guys for tuning in, and I'll see you soon.